All right, so when we talk about volumes by revolution, there are two methods for this. So this video is going to go over the disk method, and I have a few examples for you as we go through that. But first, I want to just kind of give you a visual of what it is that we're doing. And so there's two situations we have here. The first one you see right here is where it's just a single function being rotated around the axis. And so you would get a complete solid that when you spin this function around the axis, you get some sort of shape there that is uh, like almost cylindrical. The other situation, oh, let me back up. So when we do that, to find the volume of that, we are actually integrating the area of a single cross section. And a single cross section is a circle because it's being revolved. And so the area of a circle is found by pi r squared. Well, the radius of that is going to be defined by the function that you're rotating around the axis. So what you see here is the integral from a to b of the function squared, and that is multiplied by pi. And that's because we're finding the integral of the area of a single cross section. If this was being rotated around the y-axis, then we would just be doing everything here in terms of y. So our bounds would be in terms of y, and our function would be in terms of y. The other situation that we have here is when we have two functions that are being rotated around some sort of axis. And if you notice, this creates some space in the middle, so it's no longer a complete solid, but we actually we have to think about that space that doesn't exist. And so what we're looking at in this situation is finding the volume of the outer function, so that would be f of x, and then subtracting the inner function, and that's how you get that hole in the center. So here what we're doing is what I would consider the outer radius, so that's f of x being squared, minus the inner radius. And again, the radius, I would really challenge you to be visualizing exactly what it is that's being created so that you know how to define that radius properly. So let's look at a couple of different examples. I want to make sure that we go through a variety of them for your benefit. Oh, that was the wrong button. And okay, so here we go on this first example. So we've got a region bounded by this graph of y equals x times the square root of 9 minus x squared and y equals 0, and we're rotating it around the x-axis. The first thing I want to do is I want to take a look at what this function looks like, because that's going to help me identify the bounds for this. So I'm going to go to my graphing calculator, and I'm going to graph the function x times the square root of 9 minus x squared. And here I can see what this graph looks like. So if you can imagine this function being rotated around the x-axis, that's this line here, you're probably going to get a sort of hourglass shape. And the other thing I want to clarify is that this line is going to continue all the way down to the x-axis. I know that because I know this function is defined at 3 and at -3. So those are the bounds for this particular integral, -3 to 3, because that's the area that's being revolved around the axis. So let's set up my integral here. Remember that the formula is pi times the integral. In this case, our bounds are -3 to 3 of my function, x times 9 minus x squared, being squared. Okay, and this is because the radius of that revolution is going to come from the function here, and so I'm calculating the integral of the area of a circle. All right, so I've got pi r squared. Now let's work quickly through some math here. So I have this being squared, which gives me x squared times 9 minus x squared. I distribute that x squared and get 9x squared minus x to the 4th dx. And then I need to anti-derive that. So I get pi times 3x to the 3rd minus x to the 5th over 5, evaluated at -3 and 3. Then I plug in +3, and when I plug in +3, I get 81 minus 243 over 5. And then I plug in -3 and I get -81 plus 243 over 5. And then I can add these things together. That's going to give me 162 minus 486 over 5 multiplied by pi. And at this point, I got my calculator out and I got 64.8 times pi. So this is the volume of the solid that's created by revolving that line. Let's take a look at example 2. Example 2, we've got a region bounded by y equals secant of x and y equals 0. We're only looking on the interval from 0 to pi over 3. And we're revolving this around the line y equals 4. So that's important. If you remember from pre-cal, secant of x, which is the reciprocal of cosine, it has shapes like this. Okay, where this right here is at 1, and this down here is at -1, and it's got an asymptote everywhere that cosine is equal to 0. So the first asymptote is at pi over 2 and -pi over 2. Well, pi over 3 falls somewhere in here. So we know that we're revolving just this part of the graph, and it's around the line y equals 4. So y equals 4 is up here, 2, 3, 4. Okay, so here's my line y equals 4. And so we've got this shape. Okay, forgive my messy drawing, but just to give you a little bit of a visual, this right here is what's being revolved around this line, y equals 4. So it's like a flat with kind of a rounded edge on the outside. So when that gets revolved, you're going to have, I don't even know what to compare that to, a filled-in donut maybe. So let's take a look at this integral. We've got pi, we know that our bounds go from 0 to pi over 3. And the radius is what's important here, what I really want to focus on. Because this radius, again, like I said, the more you can visualize this, the easier it's going to be to set it up. So the radius for this object, when it gets rotated around, right, because it ends up on this side as well. Okay, and it's like this three-dimensional thing. So that means that the radius is the distance from this line y equals 4 to the function secant of x. So that radius is going to be 4 minus secant of x, and that is being squared. So we have pi times the integral of 4 minus secant of x squared. This here is one that I would not expect you to do by hand, so let's take a look at this in the calculator and get some practice there. So we've got pi times the integral, remember that's math and option 9, from 0 to pi over 3 of 4 minus secant, which we would enter as 1 over cosine of x squared. And then our variable of integration is x. And we get 24.980 if you cut it off, 981 if you round it up. So the volume of that shape would be 24.980 or 24.981 would be an acceptable answer as well. Let's take a look at example 3. In example 3, we've got this function here, e to the negative x. Now I realize that we have not done e, but I'm going to show you something really easy about e. Okay, the derivative of e to the x is e to the x. Isn't that great? Which means that the antiderivative of e to the x is e to the x. Whoops, plus c. So I put this in here because I figured that was easy enough to share with you quickly, and I really want to talk about how to work with exponents here. So we've got the volume of the solid generated by revolving the region bounded by y equals e to the negative x, y equals 0, x equals 0, and x equals 1. So I want to take a look at this at on a graphing calculator. So I've got e to the negative x, and e to the negative x is a decay function. we can see down here it's going to be cut off at 1, x equals 1, and up here at y equals 1. So it's like this little funnel type shape that gets revolved around the x-axis. So you're going to end up with sort of a funnel once it's revolved. So this integral here, it goes from 0 to 1, since that's the lines that are closing off that region. I'm sorry, there should be a pi in front of that integral. And then the radius here is going to be just the function e to the negative x, and that is being squared. Now remember, when exponents are being multiplied, you multiply them together, so we get e to the negative 2x. And this would be a simple kind of u substitution that you could definitely do if you wanted to work that out. But the antiderivative here is going to be negative 1/2 e to the negative 2x, because remember the antiderivative of e to the x is e to the x. This is evaluated from 0 to 1, and so I'm going to plug in 1, and that is going to give me negative 1/2 e to the negative 2. And then when I plug in 0, don't forget that anything to the 0 power is 1, so that doesn't just go away. But we end up with negative 1/2. So if I were to simplify this, and this would be important on the AP test if you had a multiple choice question, then I would end up with negative 1 over 2e squared plus 1/2. And it is possible that there is a common denominator that we get as well. So we get negative 1 over 2e squared, negative 1 plus e squared over 2e squared. Without a calculator, that would be the final answer for the volume of this solid. One last example for you. Example 4, this one here is written in terms of y, and we're revolving around a vertical axis. And so everything is in terms of y this time. So nothing changes about how we go about this process other than the fact that we're in terms of y. So x equals y squared is a sideways parabola. And this is closed off at the line x equals 4. So here is that piece there, but it's being revolved around the line x equals 5. So there's a little bit of space in between, so there's going to be a hole in the middle. And this is an example of the inner versus the outer. So as I set this up, the first thing is knowing my bounds in terms of y, and that's where this function is where they're going to intersect each other. That's the highest point. That happens at negative 2 and 2 because that line is at x equals 4. Then I take a look at my outer radius. Well, my outer radius is defined by this parabola. If I'm rotating around this axis here, the outer radius is the parabola. The line that I'm rotating around minus the parabola. So it's 5 minus y squared being squared. And then the inner radius, the one that I'm removing from that, is just this distance here, 5 minus 4. So 5 minus 4 being squared. From here, I would work this integral out. So I get 25 minus 10y squared plus y to the 4th minus 1. I can combine like terms, and I'm going to antiderive at the same time. So I'm going to get 24y minus 10y to the 3rd over 3 plus y to the 5th over 5. Evaluated from negative 2 to 2. And when I do all of the evaluation there, I did both by hand and in a calculator. In a calculator, I ended up with 174.253 as my final answer. Hopefully with these examples that was helpful for you. If you wanted to do more practice, then you can go to page 465 in the textbook, and any of the problems 1 through 35, I recommend picking a variety of them so that you can kind of take a look at the different functions and how this works. Please reach out if you have any other questions.